Hey guys, it's Miriam again with you today, and part 2 of graphing using calculus. We're going to be taking a look at horizontal and vertical asymptotes. Once again, we're going to recall from advanced functions. If we have our function f at x equals p at x over q at x, where our q at x, which is our denominator, does not equal 0, our vertical asymptote, I'll just use VA to denote it. It occurs when our q at x equals 0. And for a horizontal asymptote, I like to use an acronym that I recently learned. So one, it's what I call BOBO. I know it sounds a little funny. So bigger on bottom 0. So BOBO bigger on bottom and then just the number 0. So that means when the exponent in the numerator is less than the exponent in the denominator, so the exponent on the denominator on the bottom is bigger than our horizontal asymptote is y equals 0. The second one, this one's kind of funky. Eats DLC. I know, sort of long, but all it says is when the exponents are the same, divide leading coefficient. So our horizontal asymptote would be y equals, and a divided by c, which is we're just dividing the leading coefficients. And the third and final one, button. Bigger on top, none. So if the exponent, or the greatest exponent in the numerator, is bigger than the one in the denominator, then there's simply no horizontal asymptote. So that was a good review. Now, our horizontal asymptotes is what happens to the function as x gets very large or very small. And mathematically, using limits, our horizontal asymptote is the limit as x approaches positive or negative infinity for a function f at x. Now we have two strategies to determine the limit as x approaches positive or negative infinity. So method 1 for finding our horizontal asymptote. We're going to divide the numerator and the denominator by the highest power of x in the denominator. So what does that mean? Say we have limit as x approaches positive infinity, or 5x plus 3 over 2x minus 1. So we're going to divide the numerator and the denominator by the highest power of x in the denominator. So in the denominator, the highest power of x is x to the power of 1. So we're going to divide the numerator and the denominator by x. So that's 5x over x plus 3 over x. All of that over 2x over x minus 1 over x. Now we can see that these two x's cancel and these two x's cancel, leaving us with 5 plus 3 over x and 2 minus 1 over x. And since we're trying to find as the x approaches infinity, if we subbed infinity into the x here, that'll give us 5 plus 0 over 2 minus 0. One thing we can just sort of recall is that, say we have 3 over infinity, that gives us 0. So our answer is 5 over 2. That is our first method. Now we're going to look at our second method using the same example. So what the second method does, we factor the numerator by the highest degree of the numerator, and then we're going to factor the denominator by the highest degree of the denominator. What does that mean? So let's just rewrite it again. So 5x plus 3 over 2x minus 1. Okay, so the highest degree of the numerator is x to the power of 1, and the highest degree in the denominator is once again x to the power of 1. So in the numerator, we're going to factor the x, and the denominator will also factor the x. X, which gives us 5 plus 3 over x. X, which gives us 2 minus 1 over x. If you take a look back over here, they're the same thing because the two x's cancel out. So we're left with 5 plus 3 over x over 2 minus 1 over x, which we had here, 5 plus 3 over x over 2 minus 1 over x. So as you can see, both methods will give you the exact same answer, where we got 5 over 2. So now that we know how to determine the horizontal asymptotes, we also want to look at the behavior near the asymptote. So is the function approaching the asymptote from above or from below? And in order to do this, we have to consider very large positive and negative values of x. So using the function that we had previously, where our horizontal asymptote was y equals 5 over 2, we're going to take a very large positive number. So let's just say we take x equals 1,000. Then if we sub that into our function, we're going to get 5,003 over 1,999, which equals 2.50027. And is this greater than a horizontal asymptote? Yes, it is greater than 5 over 2. So we can conclude that f at x is approaching our horizontal asymptote, which is y equals 5 over 2 from above. And we'll do the same thing but with negative 1,000. And if we sub that into our function and we do the calculator, it gives us negative 4,997 equal negative 2,001, which is 2.497. Is that less than a horizontal asymptote or greater? It's less than 5 over 2. So therefore, f at x is approaching a horizontal asymptote, which is y equals 5 over 2 from below. And if you're having a hard time understanding this and you need a visual representation, well, say we have our graph right here and our horizontal asymptote, let's say this point is 5 over 2. Then as we approach positive infinity, which we got the x equal 1,000, f at x is approaching the horizontal asymptote from above. So what is that going to look like? It's going to be above. And then if we go to negative infinity, which we did our x equal negative 1,000, our f at x is going to be approaching our horizontal asymptote from below. So the function is going to be below it. And if we just want to summarize what we just did, I like to do if f, so positive or negative 1,000 is greater than the horizontal asymptote, then it's from above. The function approaches the horizontal asymptote from above. And if it's less than the horizontal asymptote, then the function is approaching our horizontal asymptote from below. And you can just remember this rule. Now we're going to take a look at our vertical asymptote. So as we mentioned earlier, our vertical asymptote occurs when the denominator equals 0. But once again, we need to know the behavior of the function near the vertical asymptote so that we're going to be able to graph our function. So let's take the example. We'll use a different example this time. F at x equals 3x minus 1 over x plus 5. So taking a look at it, we know the vertical asymptote occurs when the denominator equals 0, so when x plus 5 equals 0, making x equal negative 5 is our vertical asymptote. To determine the behavior near our vertical asymptote, we're going to use a chart. So let's draw a chart right over here. We have our values of x. So since our vertical asymptote is x equals negative 5, we're going to find as x approaches negative 5, from the left side, we're denoting that by the negative over here, and as x approaches negative 5, from the positive side, denoted here from the positive. So to simplify this, we're just going to take a point. So we can take x equals negative 5.0001, and here we can use x equals negative 4.999. So this is a point that's to the right side of negative 5, and this one's to the left side of negative 5. So we'll take our numerator, 3x minus 1, our denominator, x plus 5, and then our overall function, because it's 3x minus 1 over x plus 5. And then in this last column, we'll be able to write what the behavior is. So if we take negative 5.0001 and we sub that into 3x minus 1, you put into your calculator, you'll get a negative number. If you put negative 4.999 into 3x minus 1, once again, you'll get a negative number. You do the same thing for x plus 5, so negative 5.0001 plus 5 gives us a negative, and negative 4.9999 plus 5 gives us a positive. And now for the overall function, so since it's 3x minus 1 divided by x plus 5, negative divided by negative gives us positive, and negative divided by positive gives us negative. So this tells us as f at x, it's going to approach, since it's positive, it'll be positive infinity. And since it's negative, it'll be negative infinity. To visualize this, we're going to draw a graph. So say we have our vertical asymptote, x equal negative 5. As we approach it from the left, which was this row over here, it's going to go, our function will go to positive infinity. See, positive infinity. And if we approach it from the right, which is this row over here, it'll approach negative infinity. So as a general rule to remember, we can summarize what we did. So if our values of x, if x approaches the vertical asymptote from the negative side and from the positive side, so if it approaches it from the negative side, it's positive, it'll go, the behavior of the function will go to positive infinity, and if it's from the negative side, it'll go to negative infinity. So that's just a little table you can use to remember how to find the behavior as the function approaches the vertical asymptote.